Let us look at center of a group. The center of a group G is a set of all those elements of the group G which commutes with every other element of G and is represented as Z of G. So this is written as Z of G is equal to the set of the elements in G where for all x in G, Z times x is equal to x times Z. Let's look at some properties. Now Z of G, that is the center of the group, is always normal subgroup of the group G. Now if Z of G is equal to G, that means all the elements of G commute with each other. Then G is abelian. Now if Z of G is equal to a set containing only E, the group has a trivial center. We know E always commutes with all the other elements. What this means is that no other element commutes with each other. Let's look at some examples. Z of S2 is equal to S2 since S2 is abelian. Z of S3 is equal to only E because E commutes with everything. The two cycle transpositions do not commute with each other. So 1, 2 times 1, 3 is not equal to 1, 3 times 1, 2. Similarly, three cycle permutations 1, 2, 3 and 1, 3, 2 do not commute with each other. Now let's look at another example. The center of Q8 is equal to 1, minus 1. Let's go into more detail with respect to this. Now we know Q8 is equal to 1 minus 1 I minus I j minus j k minus k under the group operation. So now here for all x in Q8, x times 1 times x inverse can be written as x times x inverse, which is equal to 1. So that means this commutes. Similarly, x times minus 1 times x inverse is equal to minus x times x inverse, which is equal to minus 1 for all x in Q8. So again, minus 1 also commutes with all other elements. So we can say that 1, minus 1 is a subset of Z of Q8. As of now, we are just saying it is a subset because we also have to look at other elements, whether some of the other elements commute with each other. So let's take J times I equal to I times J. Now, is this correct? We know I times J is equal to K and J times I is equal to minus K. That means it doesn't commute. So I cannot be in the center of Q8. Similarly, J, K minus A minus J minus K are not in the center of Q8. So the set containing 1 minus 1 is a subset of Q8 and plus or minus I, plus or minus J, plus or minus K are not in center of Q8. So which implies Z of Q8 is equal to 1, minus 1. Now let's look at another example. Let's look at the group D2N, dihedral group of order 2N. Now D2N is equal to the group generated by rotations and reflections, where r to the power of n is equal to E, s square is equal to E, s times r times s is equal to r inverse. Let's relate it to geometrical figures. So in that case, n is the number of sides of the regular n-gon and 2n is the sum of rotations and reflections. So order of D2n is equal to 2n, R is equal to rotation by 2 pi by n. And S is the reflection across n lines of symmetries. So if we are talking of an equilateral triangle, then in that case, order of D2n will be 6. R would be equal to rotation by 360 by 3. That is 120 degree. And S will be the reflections across n lines of symmetries. That is 3 lines of symmetries of an equilateral triangle. Now here, all rotations commute with each other. Let's see, r to the power of A times r to the power of B. Since they both are rotations, we can combine them. So r to the power of A plus B. And since addition of integers is commutative, we can write this as r to the power of B plus A. And again, we can split it and say r to the power of B times r to the power of A. So r to the power of A times r to the power of B is equal to r to the power of B times r to the power of A. So that means they commute. Rotations commute. Now a rotation r to the power of k commutes with a reflection s only if s times r to the power of k is equal to r to the power of k times s. Very clear. Only if these two are equal, then only we can say r to the power of k commutes with s. Now let's go a little bit more in detail. S square is equal to E. That's a part of the definition of the group itself. Which means we can say S is equal to S inverse. Now let's take the other part of the definition. S times R times S is equal to R inverse. Now S and S inverse are inverses of each other. So we can write this as S times R times S inverse is equal to R inverse. Conjugation respects powers. So S times R to the power of K times S inverse is equal to S times R times S inverse to the power of K. And since S times R times S inverse is equal to R inverse, we can write it as R inverse to the power of K. And we can simplify it to R to the power of minus K. Right multiplying on both sides by S. What do we get? S times R to the power of K times S inverse times S is equal to R to the power of minus K times S. Simplifying this, we get S times R to the power of K. When we compose these two, we get E. That times this will give us S times R to the power of K is equal to R to the power of minus K times S. A rotation of R to the power of K commutes with S if and only if R to the power of K is equal to R to the power of minus K. See, only if these two are equal, then S times this and this times S will be equal. So let's see under what condition will they be equal. Let's bring it to this side by right multiplying by R to the power of K. We get R to the power of K times R to the power of K is equal to R to the power of minus K times R to the power of K is E. Now, this becomes R to the power of 2K is equal to E. And now we solve R to the power of 2K is equal to E. So now here, if N is odd, the only solution is K congruent to 0 mod N. That is R to the power of 0 is equal to E. Because if we say K is 0, that means 2K is 0. So R to the power of 0 is equal to E. So that means when N is odd, the center of D2N is equal to a set containing only the identity. Now, if n is even, then k is congruent to 0 mod n, or k is congruent to n by 2 mod n. Because if you substitute n by 2 here in k, 2 times n by 2 is n, and r to the power of n is equal to e as part of the definition of d2n. So that means z of d2n, that is the center of d2n, is equal to e and r to the power of n by 2 if n is even. So what does this mean? It means that d3, the center of d3, is just the element e. And here remember, when we say d3, we are thinking geometrically in terms of n-gons. So in that case, it would be an equilateral triangle. If it is a square, then the center will be e and r square. If it is pentagon, it will be only e. If it is hexagon, e comma r cube, and so on. That was center of a group. Remember, these are normal subgroups in their respective groups, because center of a group is always a normal subgroup of G. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.